Hello, and in this video I want to take a look at this tricky question here. It's to do with oblique collisions with walls, right? So we've got this diagram, we've got this question here, and we need to get this sort of expression, right? This sort of horrible, scary looking expression. Okay, so I'm not going to read the whole block of text out, but essentially what's going on is there's multiple collisions, right? So firstly, this object we're dealing with, this particle P, hits the wall BC there, okay? Then it's going to hit the wall AB, so it's going to look like that, okay? And then it's going to collide with the wall AB there, and then it's going to further collide again with BC somewhere there, okay? Now, I just want to explain. The mark scheme is a bit brutal here, because you need to be careful where the trajectory is. Okay, so it's not going to rebound to the left like that. It's going to rebound to the right like that instead. Okay, and you will lose, I think, 2 accuracy marks if you do it the wrong way. I did it the left, and then I had a look at the mark scheme. Ooh, that's not technically right. You can't say it goes to the left, like that. It won't bounce off the wall to the left, because if it bounces to the right, then the angle afterwards, I'll call this beta, right? It has to be smaller than the original angle here, okay? With collisions, right? So if I do a general sort of diagram, okay, for general collision, the angle before alpha and the angle afterwards beta, okay, in a collision, the angle is always reduced. That is because if you were to do the equations, you'd ultimately deduce that tan beta is E lots of tan alpha. But the thing is, E is less than or equal to 1. So that means tan beta would be less than or equal to alpha. So beta is less than or equal to alpha, which is saying that the angle is reduced. Okay, so the angle afterwards has to be smaller. Okay, so hopefully you can see it's smaller here. If we was to go to the left, okay, instead, it would be quite a big angle. Okay, it's going to be bigger than the original angle we started off with. So the mark scheme is a bit technical. You have to go to the right like this, okay, at this angle here, right? Okay, so hopefully that made sense. Hopefully clarified that. I assumed it went to the left because that's how my mind works. I'm not the most physicsy person, but it actually does matter with this particular question. You will lose 2 marks if you don't. The maths works out fine. You would still be able to get this equation and do the question, but they're a bit picky. Okay, but technically it should be going to the right. Anyway, so the trajectory is gonna look like that, and then it's gonna bounce off the wall again like that. Now what we're told is that when it hits the wall BC here the second time, we're told it's moving perpendicular to the wall. So it's gonna hit the wall at a right angle, right? At 90 degrees. Okay, at that second collision. Okay, so when it hits the wall BC here, the second time it's at a right angle. Okay. Now, if we focus on the first collision here then, well, what is the angle here? What's the angle it approaches at before? Well, actually, you need to realise this is going to be theta as well, right? Because, and you can deduce this in many ways, but I guess one way to see it is actually look that we have a sort of F shape here, okay? And we've got these 2 sort of parallel lines, okay? So if I draw that shape out here then, this sort of F shape we've got, think back to GCSE when you looked at angles on parallel lines, okay? So this angle here is theta, which corresponds to the theta here. And then this angle also has to be theta, okay, which corresponds to the angle there. Because they're corresponding angles, or the F angles, okay? But hopefully you can see that. But yeah, so there's many ways you can see that, but you need to recognise we're going to actually approach with the same angle theta there. Okay, so hopefully with me here. Obviously the angle afterwards is beta, okay, we just label it beta. Then let's look at the second collision here, okay? So we've got these 2 collisions. Well, the angle it's going to approach at is here, okay? And then the angle it leaves is going to be that angle there. Now, actually, this angle here we can work out quite nicely because recognise we've got a triangle, okay? We've got this triangle here. So if I were to draw that out, okay, we've got this angle theta and then a right angle triangle, and then a right angle, sorry. Well, then we can easily work out this remaining angle here because it's going to be 180, take away the two angles because angles in a triangle add up to 180, right? Hopefully happy with that. So therefore, 180 take away theta, take away the 90 degrees is going to be 90 take away theta, and that's going to be my angle there. Okay, so hopefully with me here, so I can label this angle to be 90 take away theta there. So then I just need to work out an expression for the angle here before the collision, right? Okay, so I'm gonna have to look at my angles then. But the thing that strikes me is I've got a triangle here, right? So I can work out this angle in orange. Okay, if I was to draw that triangle out, okay. Well, we have a right angle there. Okay, we have a right angle, and we have the angle, beta here, right? Hopefully you can see that. So the angle here, well, again, it's going to be 180 take away the other two angles, so it's going to be 90 take away beta. Okay. So the angle in orange then has to be at 90 take away beta. Okay, so hopefully you're with me here. And so therefore we can work out this angle then. Okay, because recognise if I do it in blue, we've got angles on the line. Okay, so angles on the line also have to add up to 180. So therefore the angle I want is going to be 180 take away this angle here, so 90 take away theta, and then also take away the orange angle, 90 take away beta. If we simplify this, you're going to get theta add beta. Okay, so there we are. So this angle is theta add beta. Okay, so hopefully you're happy with that. Okay, and so there we are. So I've labelled my angles now, so I can actually proceed to just do my usual stuff now and do my consider the parallel and the perpendicular equations for each collision, as we normally do with these sort of questions. And so there we are. So that's probably the trickier part of, maybe I'd say, just to work out the angles here, but hopefully you're happy with the angles we've got. Okay, the angles we've got here. So from here on out, I'm just going to do the standard stuff. So firstly, if I consider the first collision. So firstly, the parallel equation. I'm not going to label the parts. Hopefully, again, you're fairly comfortable with a collision questions like this now. So I'm just going to jump into it. So the parallel part for this collision, right? Firstly, if I label the speeds then, let's say the initial speed is u, and then the speed is v, okay? So v cos beta afterwards has to be u cos theta, because again, the parallel parts are the same. Then for the perpendicular parts, v sine beta has to be e lots of the original u sine theta, okay? Then what we can do is we can then divide the equations as we normally do to get tan. So v sine beta over v cos beta on the left has to be eu sine theta over u cos theta on the right. And so that simplifies to tan beta to be e tan theta. And there's my equation there. So hopefully happy with that. Then I can do the same thing for the second collision here. Okay. So if I do my parallel equation first, so remember what we're looking at now with the second collision, okay, we've got the angles theta and beta, and then the angle 90 and 90 take away theta, Okay, those are the angles before and after. Therefore, firstly, the parallel equation is going to be W cos of 90 take away theta afterwards. That's going to equal V cos of theta add beta before. Okay, so hopefully happy with that. Okay, then perpendicular. So that's going to be W sine of 90 take away theta. Again, that's going to be E lots of the original V sine of theta add beta. Okay, so hopefully happy with that. So V and W are my speeds before and after, and theta add beta is my angle before, and 90 take away theta is the angle after. So I'm just applying the same sort of equations, the same stuff, but with the angles and stuff here. Hopefully with here. So at that point, at this point, all I've done was the same sort of equations. Okay. But yeah, and so then again we can divide the equations. So W sine of 90 take away theta to be, and then over W cos of 90 take away theta. That's going to be EV sine of theta add beta over V cos of theta add beta. And then obviously this will reduce the tan. Okay, because tan is sine over cos, right? So tan of 90 take away theta to be E lots of tan theta add beta. Okay, so I'll get this equation here, right? Hopefully you are happy up to this point. Right, so firstly we're going to simplify the left tan, right? So tan of 90 take away theta. Okay, so we need to simplify or sort of expand that. Okay, now I can't use the tan compound angle formula for this, okay, because you would have to do tan 90. So if you was to apply the formula here, that'd be tan 90 take away tan theta over 1 plus tan 90 tan theta. You can see the issue here. We're going to need tan 90, which is undefined, but we can still simplify it if we just say sine over cos instead. So this is the same as sine of 90 take away theta over cos 90 take away theta, right? Because tan is sine over cos, and then we can simplify the top and the bottom. So we can use the compound angle formulas for sine and cos instead. Okay, again, hopefully you're familiar with that from normal maths in year 2. Okay, so hopefully you're happy and you're convinced that if I expand this, this will go to sine 90 cos theta take away cos 90 sine theta all over cos 90, and then on the bottom cos 90 cos theta plus sine 90 sine theta. So hopefully happy with those expansions. Again, look back to the formula book as I've shown you there. And then we can simplify because we know what sine and cos 90 is. Sine 90 is 1 and cos 90 is 0. So this will simplify to cos theta, over sine theta, which is quite nice because that is what? 1 over tan, right? Because tan, remember, is sine over cos, so we're flipping it to get cos over sine. So it's 1 over tan. So tan of 90 take away theta is just 1 over tan. Okay. And there we are. So hopefully happy with that. Then if we look at our equation, okay, now we need to simplify tan theta add beta. Okay. So I'm going to do that down here. And again, we're going to need to look at our formula book, our compound angle formulas. Actually, we can just use tan, right? There's no 90 degrees. We can just use the tan compound angle formula, okay? So if you look at that, hopefully happy that tan of theta add beta, okay? If you substitute that into the formula, hopefully happy that will go to tan theta add tan beta all over 1 minus tan theta tan beta. But hang on, if we look back at our workings, we know what tan beta is. Tan beta from the first collision, tan beta is E tan theta. So we can substitute that in as well. So that will go to tan theta, add tan beta, which is E tan theta, over 1 minus tan theta, tan beta, which is E tan theta. And actually that will go to tan theta, add E tan theta, over 1 minus tan, 1 minus E tan squared theta. And there we are. There we are. So, cool. So tan theta add beta actually just goes to tan theta add E tan theta over 1 minus E tan squared theta. So now we can substitute these results, okay, these simplifications into my main equation here, right? So firstly, on the left, we have tan 90 take away theta, which goes to, as we've seen here, 1 over tan theta. So on the left, okay, on the left side, that's going to be 1 over tan theta, okay? Then on the right, it's going to be E lots of tan theta add beta, which we have seen goes to tan theta add E tan theta over 1 minus E tan squared theta, okay? So tan theta add E tan theta over 1 minus E tan squared theta. And then we just need to simplify, okay? We need to simplify. So if I expand the sort of bracket on the right, that's going to be E tan theta add E squared tan theta over 1 minus E tan squared theta. Then obviously we just got two fractions, so we can cross multiply if you want to simplify. If you simplify this, then that's going to be 1 minus E tan squared theta to be tan theta of E tan theta plus E squared tan theta. Then if we expand on the right, we're going to get E tan squared theta plus E squared tan squared theta. Then let's move this minus E tan squared to the right. Okay, so just 1 is going to equal E tan squared theta add E tan squared theta plus E squared tan squared theta. Then notice I've actually got like terms, right? I've got 2 lots of this E tan squared theta. So we can get 1, which is 2 lots of E tan squared theta plus an E squared tan squared theta. Okay. Then what can I do? I can actually factorize the right. Okay, so actually a common factor of E tan squared I can pull out. Okay. And then that would be 2E, 2 add E, right? Then if I rearrange ever so slightly, I get E lots of E plus 2 tan squared theta to be equal to 1. And that should be the equation they wanted me to get, okay? And so indeed, that's exactly the expression they wanted from me there. So that's part A done for 10 marks. Fairly tricky, that is, I'd say. But actually, once you get past the angles right at the start, once you've found your angles, hopefully you can see it's sort of standard-ish from there. So once we found our angles, then we just consider the perpendicular and the parallel equations like we always do with these sort of questions. And then we did the same sort of trig identities afterwards to simplify our expressions. So we used these sort of trig identities, our compound angle formulas, and then simplified to get the expression I wanted, okay? So hopefully once you got past the angle business at the start, hopefully it wasn't too tricky of a question. Again, if you practice some of these sort of questions, it's actually the same sort of techniques really, where you do your equations, then you use the trig identities, and you simplify to get the answer they want. But there we are. That's part A, okay, for 10 marks. Then part B says, deduce that for the motion to be possible, the angle between the walls must be at least 30. So the angle between the walls, that's actually the angle theta, okay, as you can see there, between the walls. So that's saying theta has to be at least 30 degrees, okay. Now, obviously we're probably going to have to use part A. They've probably asked us to do that for a reason, right? So if we look at part A then, so we've proven that e lots of e plus 2 tan squared theta equals 1, okay? And we sort of want to get theta, okay? Almost like solving for theta. So if I rearrange to just get tan on its own then, so tan squared theta is going to be 1 over e of e plus 2. Now, where do we go from here? So again, if you look back, remember, I want theta to be greater than or equal to 30, okay? So I want an inequality for theta here, okay? But I also want to get rid of the e. Well, I want an inequality and I want to use e. So I'm probably going to have to use the standard inequality, e being between 0 and 1. And again, that's a very common technique, okay, with collisions where you're going to need to exploit this inequality for e, okay? You really should have this at the back of your mind, but there we are. So we're going to use this then, and actually technically e can't be 0 here, so it has to be strictly greater than 0, because if you look back at the diagram, right, that has to bounce off the walls, okay? It has to be some sort of verticality. It has to bounce off the walls, because if e was equal to 0, it would only be parallel, okay? It would only move along the wall, okay? Because there wouldn't be any perpendicular component, because the perpendicular component involves e. So e can't be 0 because it has to actually bounce off the walls for this motion to happen, okay? It can't just stick to the wall, okay? But yeah, a pretty technical point. Actually wouldn't affect our answer, it turns out. But I'm not too sure how harsh the mark scheme would have been for that. But there we are. Anyway, this is the inequality we're going to work with e. Okay, so hopefully with me here. So obviously I've got e, but I want this expression here. I want 1 over e of e plus 2. So how on earth am I going to get to that? Okay, well then let's do e plus 2. Okay, so if I add 2 to both sides, that's going to be e plus 2 being between 3 and 2. Okay, so hopefully happy with that. And then we want to multiply them, right? We want to do e of e plus 2. So e of e plus 2, well, we can sort of effectively multiply the inequality, right? So if we multiply the left side, 0 times 2 is 0, so it's going to be between 0 and then less than or equal to, then 1 times 3 at the other end. 1 times 3 gets me 3. Okay, so hopefully happy with that. Then of course I want to sort of do the reciprocal. I want to divide by e of e plus 2. So now if I divide by e of e plus 2 to both sides, well, firstly, 0 divided by e of e plus 2 is still 0, right? Divide anything by 0, divide 0 by anything, it's still 0, right? So 0 on the left, then e of e plus 2 divided by itself is just 1, okay? And then we've got 3 over e of e plus 2. So hopefully you're with me here, okay? And so really the only thing I can deduce here at this point is actually that 1 is less than or equal to 3 over e of e plus 2. Okay, and then I can reverse that, right? So then I can flip it to say 3 over e of e plus 2 is actually greater than or equal to 1. Okay, now we're very nearly there. Okay, to match the expression, I don't want 3 over that, I want 1 over that. So I can just divide it by 3. Okay, so I can divide the inequality by 3, and therefore that gets me 1 over e plus 2 is greater than or equal to 1/3. And there we are. And so that's tan, right? That's tan squared. So 1 over e of e plus 2 is tan squared. So therefore, we have tan squared now being greater than or equal to 1/3, which is great news because the e goes away. And we can now solve for theta quite nicely. So how would you solve this for theta? Well, you can square root to just get tan squared. To get rid of the tan squared to just get tan to be greater than or equal to root of 1/3. And then you can do inverse tan to get theta. Inverse tan of root of 1/3. If you put that in the calculator, it's exactly 30 degrees. And so therefore we get theta to be greater than or equal to 30 degrees. And there we are. So we got to what they wanted us to show. Okay, and there we are. So again, so we use the inequality for E to get the inequality they wanted at the end there. But there we are. So overall, again, fairly tricky question, but hopefully that has helped. But there we are. I'll see you next time.